Here we will attempt to provide some very simple insights into Einstein's special theory of relativity. Relativity deals with how the measurement of distance and the very flow of time itself is different in different frames of reference. The following fact might surprise you because it is so counterintuitive. If we watch a car moving down the street, its clock runs slower than ours, and the 1-foot ruler in the car is less than 1 foot measured against our ruler. The starting point into the theory of relativity is a surprising one. The speed of light is constant. No matter how fast you move, no matter what direction you move in, the speed of light relative to yourself always has the same value, approximately 300 meters each millionth of a second. We are now going to perform an experiment. A spacecraft traveling at 1/2 the speed of light is going to make a very close pass near the top of a tower. As soon as it grazes the top, a nuclear photon generator on the tower will produce the most brilliant, most powerful pulse of light. We will first observe the experiment with our unaided eyes. Remember that the spacecraft is traveling at 1/2 the speed of light. That's about 90,000 miles per second, so don't blink. Okay, here goes. Obviously, the spacecraft went by too quickly to see anything. We also recorded the scene with some very special high-speed cameras which can assemble a picture as though the entire scene were captured in one instant. And here's the result. There's the spacecraft. We'll stop the action in exactly 1 microsecond. In that time, the bubble of light expanded to approximately 300 meters, or approximately 1,000 feet, and the spacecraft, moving at 1/2 the speed of light, moved 150 meters past the tower. Now, let's add some clocks into the ground frame and into the spacecraft frame. The clocks will start running the instant the flash is triggered. 1 complete rotation of the hand is 2 microseconds. The ground clocks read 1 microsecond. The radius of the sphere is 300 meters, and geometry tells us that the height of the bubble of light directly above the spacecraft is 260 meters. Let us focus on the light above the spacecraft. Since the spacecraft is moving horizontally, relativity has no effect vertically. Thus, at this moment, the spacecraft people observed light to move 260 meters from the flash point straight up. Remembering that light goes 300 meters each microsecond, their clock must be reading a little under 1 microsecond. To be exact, 0.866 of a microsecond. Thus, notice the amazing result. Clocks moving relative to ourselves run slower. This is a consequence of nature, demanding that the speed of light must always have the same value. Let's add a clock into the spacecraft frame opposite the tower and call it clock D. We've seen already that clock B reads higher than clock A by 15%, as a matter of fact. Next, imagine being on the spacecraft and watching the tower go by. If you think about it, that is exactly equivalent to being on the ground watching the spacecraft go by. All the numbers we arrived at before would now still be the same, but the other way around. Clocks A and C are special. They were at the exact same point at exactly the same time, the point where the flash occurred. Well, clock B, which is now opposite to clock A, reads higher than clock A, and thus so will clock D be higher than clock C by the same amount, and that amount is 15%. Thus, clock D must read 1.15 microseconds. Well, if that's so, then the tower must have appeared to have moved, as seen from the spacecraft of course, 173 meters, as given by distance equals velocity times time. Now notice the amazing result. The 173 meters in the spacecraft frame exactly matches 150 meters in the ground frame. Thus, a meter in the spacecraft is shorter than a meter on the ground. And this is the second important feature in the special theory of relativity. Distances shrink in the moving frame. But remember, from the spacecraft, it's the other way around. Distances on the ground seem shorter. Next, an unexpected observation. If the moving clocks always run slower, how can clock D read higher than the ground clocks? The answer is in the synchronization. Relativity is full of surprises. Let's rerun the scene. Watch the clock on the left and note when it starts. No wonder that clock reads high. It started too soon. Actually, if you had watched the synchronization process from the spacecraft, all spacecraft frame clocks would have appeared to start simultaneously, as they are supposed to in that frame. And there's the third interesting feature of relativity. Events which are simultaneous in one frame of reference are normally not simultaneous in any other frame. And thus, we have shown in a simple geometric fashion the three main features described in the special theory of relativity. Time runs slower in the moving frame. Distances shrink in the moving frame, and simultaneous events in one frame are not simultaneous in other frames.